Today's lesson is on simplifying radicals. This is the second half of Unit 7, and even though it says radicals, you are going to find out over the next couple of days why radicals fit in the same unit with the laws of exponents. But let's start out with today's lesson, which is I can use square roots and properties of exponents to simplify expressions. This is your title, Simplifying Radicals. This is your learning target. Get that in your notes, and then we'll continue. We're going to start out with some simple square roots that you should probably remember from middle school. The square root of 16 equals 4. But let's talk about that. That is because 4 to the second power, which we could call this 4 squared. So if you hear somebody say 4 squared, they really mean 4 to the second power. And when we do the reverse of that, that equals 16. When we do the reverse of that, we say the square root of 16 equals 4. So these two things go together. What you don't see in the second part is this symbol. This radical, there is an understood 2 right there. So far in everything we've done this year in math, we've had an understood 1 for x is 1x. We've had an understood exponent for just 4, the exponent's 1. But for a radical, the understood root, the understood index is 2. So on this top row up here, this is all understood to say, what can I use 2 times to get this answer? So I can use 4 times 4 to get 16. Right here, I can use 7 times 7 to get 49. So the square root of 49 is 7. And I can use 10 twice. 10 times 10 is 100. So the square root of 100 is 10. I am going to show you that you can have different roots. You can get the cube root of 8. So that is not asking you what you can use twice to get 8. It's asking you what can you use 3 times. In this case, 2 times 2 times 2 equals 8. So the cube root of 8 is 2. And this one has the 4th root. So we know 9 times 9 is 81. But that's not it because I'm only using 2 numbers. What the 4th root is 3 times 3 times 3 times 3. That equals 81. And that's what I used 4 times to get 81. So the 4th root of 81 is 3. In the next few lessons this week, you are going to be focused on these kind. You're going to be focused on the understood root of 2. Square root. These are the common perfect squares all the way from 1 times 1, which is 1, 2 times 2, square root of 4 is 2, 3 times 3, square root of 9 is 3, all the way up to 20 times 20, the square root of 400 is 20. You may want to pause the video and write these down. These are some things that we are going to refer to a lot. You, of course, have this image in your Unit 7 slides, so you can look at it anytime you need to. It is an option that you will be able to refer to on all assignments, on your quiz, on your test for Unit 7. But as a student, I always found it helpful if I had it written down in my own notebook, I could just flip right to it. So some basic vocabulary. As you heard me say, this little number in the corner of the radical sign is called the index or the root. Most of the time, I will call it the root. But if you hear someone talk about the index number, that's the number in the corner of the radical symbol. Speaking of, this little check mark box, where we usually call it the square root box, that's called the radical symbol. So that's why you hear us calling this part of the unit simplifying radicals. The number that's inside or under the radical is called the radicand. Don't forget, that we're going to be focusing on just this. This is the square root. You will not see the 2 written in because that is understood. So on the upcoming problems, you will just see this symbol, but this is understood to be the same as a root of 2. What can we use twice to get what's under the radical symbol? So when it's a perfect square underneath, it's pretty easy to evaluate a square root. What can I use twice to get 25? 5. So the answer to the square root of 25 is 5. What can I use twice to get 121? 11. So the square root of 121 is 11. It gets a little harder when what's underneath the radical symbol is not a perfect square. So you can see I have down here in the corner, I have a few of the radicals that I use the most often. And what you want to do when it's not a perfect square, you want to separate it into 2 things that maybe one of them is a perfect square and one of them is not. So I know 50 is 25 times 2. So I'm looking in my radical cheat sheet and 25 is a perfect square. So I'm going to call this the square root of 25 times the square root of 2. 25 times 2 is 50. So this expression is equivalent to this expression. But what I've done now is I've given myself the square root of 25, which I know what that is. 5 times 5 is 25. So that part has an answer of 5. Square root of 2, it's not 4. You don't go backwards. Square root of 1, I know. Square root of 4 is the next one I know, but I don't have a quick answer for the square root of 2 or the square root of 3. The next one I know is the square root of 4. Since I don't have a whole number answer for the square root of 2, I leave the square root of 2 underneath the radical symbol. The next one that I have is the square root of 54. Square root of 54 is somewhere between 49 and 64. 7 times 7 is 49. 8 times 8 is 64. So if I put the square root of 54 in a calculator, I would not get a whole number. So let's look at that real quick. Here on my Desmos calculator, if I look right inside here and I look for in the keyboard down here, I look for the square root. This is it. And I put 54 in there. It gives me this long, ugly decimal. Lots of students would like to put this down and say 7.3 or 7.35. And many, many times rounding off this decimal is perfectly acceptable. But sometimes we want an exact answer, and an exact answer is not a rounded off answer. So you'll find as you go through higher mathematics classes and higher science classes, especially those that lead to scientific research, you want an exact answer. So we don't want 7.3 for 54. We want exactly, but we want it to be more understandable. I can understand 5 times something is the square root, and I can find something for 54. So I look in here and I'm going, so it's between 49 and 64. It's not one of those. So I'm going to go to a lower number and see 36 times something. It's not 54. 25 times 1 times 2, not 54. 16 times 4 times 3, no. 9 times 6. 9 times 6 is 54. So this is the square root of 9 times the square root of 6. I know the square root of 9 is 3. The square root of 6 I do not have over here. So 3 radical 6, or 3 times the square root of 6, is the simplified version for 54. We're going to do that one more time. Square root of 48. In my cheat sheet, 49 is the closest, but it's not it. So I'm going to back up and see if there's anything else that goes into 48. 36 is kind of too big. 25 times 2 is 50. 16 times 3 is 48. So I'm going to use 16 times 3. I do know the square root of 16 is 4, but the square root of 3 is not a whole number. So I'm going to use the square root of 3. Now, this one right here, 16 times 3, the part that I broke it down to, most students don't have 16 times 3 memorized. You might have 9 times 6 because that's in your multiplication tables that you should have all the way from 1 times 1 to 12 times 12. So 9 times 6 equals 54 should have been in your memory. 16 times 3 might not have been. So hang on. I'm going to show you, besides knowing all of the square roots, I'm going to show you a way that you might still be able to answer questions like this. So we're going to talk about two ways. One way is prime factorization, which I find that many students like to use. And then other students who are excellent with their multiplication tables, they might prefer to use perfect squares. So I'm going to do perfect squares first. My number is 18. And so I come down here, there's 16 and 25. So I'm going to go backwards from 16 and see if one of the perfect squares goes into 18. And I do see this one, 9. So I'm going to do 9 times 2, square root of 9 times the square root of 2. I know the square root of 9 is 3, so 3 radical 2. Another way is called prime factorization. Prime factorization is where you go a little bit farther than I just did, and you're looking for, what's that understood number? 2. You're looking for sets of 2 of the same number. So I'm going to take my 18, and I'm going to say that's 9 times 2. So it's not too much different than this. But when I'm doing prime factorization, I'm not thinking about this has a square root. I'm just thinking about breaking everything down as far as I can. So that's 3 times 3. Now, 2 is a prime number. 3 and 3 are prime numbers. That means nothing else goes into them besides the number 1. So I stop right here. Those are the ends of my branches. And then at the ends of my branches, there is 2 3s. And remember, I'm looking for 2 of something. Since there are 2 3s, a 3 gets to come out from under the radical, but there is only 1 2. He does not have a partner, so he has to stay under the radical. I get the same answer, but lots of times when you're not thinking of what those perfect squares are, and guys, I know this is really tiny on your Chromebook, but you should have written some of these down when we first started. This is all I'm referring to over here in the corner. So I'm going to go ahead and make that a little bit bigger this time when I'm getting ready to work. And you have your options again, prime factorization and using perfect squares. Again, I'm going to start on the using perfect squares. I'm going to look at this chart that I have, and there's 225. I don't have anything bigger on my small sheet here. You might have something bigger in your notebook because I skipped a bunch of numbers. I just stopped at 15 here, but I'm going to go backwards. 196. I don't think that goes into 300. 169. 144. Probably not. 121. No. 100. 100 times 3. That's easy. So I'm going to rewrite this as the square root of 100 times the square root of 3. And I'm going to say the square root of 100 is 10. Then radical 3. So that's my answer. On 300, I might even do the same thing. I might use my prime factorization. I might even still do 100 times 3. 3 is a prime number. And then when I do 100, I get 10 times 10. 10 and 10 are not prime numbers, but don't forget, I am looking for 2. So I just found a pair of 2 of the same factors. That means 10 gets to come out from under the radical. 3 does not have a buddy, so 3 stays under the radical. Same answer, just a different way of thinking about it. Let's look at another one. 512? All right. So I'm going to have issues with 512 because my brain doesn't like 196 times something might be 512. 169 times something might be 512, but my brain does not think in square roots on a regular basis. So here's what I notice. I notice that it ends with a 2, which is an even number. So I'm going to go to my calculator and I'm going to do 512 divided by 2 and see if that's something that I can deal with better. 512 divided by 2. 256 is also an even number. So while I'm here, I'm going to divide that by 2. And I got 128, still an even number. So I'm going to divide that by 2. And that's 64. So I'm going to come back to my problem. And when I used my calculator, 512 was 2 times 256. And that doesn't break down anymore. 256 was 2 times 128. That doesn't break down anymore. 128 was 2 times 64. There's another 2. And 64 is 8 times 8. Now, 8 and 8 are not prime numbers, but it's a pair. So I have a pair of 8s. I also have a pair of 2s. Then I have this 1, 2 that doesn't have a pal. So I get to take a 2 out because there was a pair of 2s. And I get to take an 8 out because there was a pair of 8s. But this 1, 2 without a buddy stays underneath the radical. Then I do the outside. 2 times 8 is 16. Radical 2. Final answer. Now let's look at 147. This one's a little bit harder because 147, that's not an even number. So it won't divide by 2. I'm going to try to divide it by 3. So I'm going over to my calculator and I'm going to take 147 and I'm going to see if it'll divide by 3 and see if I can get that factor tree going because my brain is not thinking in square roots. So 147 divided by 3. Now that worked out, guys, and I'm really happy to see that 49 because I know the square root of 49. But if you can't find a number that goes in, if 2 doesn't go in and 3 doesn't go in, then next I would try 5. And if 2 and 3 and 5 don't make your number divisible, then the next thing I would try would be 7. So what you've seen me do is I did a number where I tried dividing by 2. So this is where I divided this one by 2. This one, I just divided it by 3 because it was not an even number. So I'm going to do 3 times 49. But when I'm writing down the 49, I remember that is in my radical chart. It's right here. The square root of 49 is 7. It's already in something that I know. So I'm going to do this the square root way. I'm going to say the square root of 49 is 7, and radical 3 is left on his own. If I didn't do it that way, I would have done, keep going, and you can certainly do this. 3 times 49, that's a prime number. 49 is 7 times 7. Those are prime numbers, but we found a pair. So the 7 comes out and the 3 stays in. 7 comes out, 3 stays in. Those are simplified radicals. Now, what happens if there's an extra number in front? No big deal. You just have to keep track of it. This means I want to do -2 times whatever this is. So I'm going to do -2 times the square root of 20. The square root of 20, the first thing I thought of was 4 times 5. 5 is a prime number. 4 equals 2 times 2. That's a pair. Remember, I have that understood 2 right here as my index or my root. Since I have a pair of them, that 2 gets to come out with the negative 2. That's already out here. But 5 is going to remain under the radical. So I have the negative 2 that was already on the outside or in front. Then I have this 2 that had a pair inside the radical, but I still have this 5 that does not have a pair. Then I simplify because I can do negative 2 times 2, which is negative 4. And you will hear some people call this negative 4 square root of 5, negative 4 radical 5. But you've got to say something to indicate that you know the 5 is underneath this radical symbol. Now let's look at this one. 7 times 288. When I look at 288, I do know that that's 144 times 2. That does not always pop in my head. 144 is a perfect square. That is made from 12 times 12. So that popped in my head. So I know that a 12 can come out and the 2 would stay under because he doesn't have a partner. But let's say that doesn't come in your head. Let's just say you start dividing by 2. Well, I'm going to get 2 and 144. But let's say your brain's not focused on perfect squares. So then you go again and you say that this is 2 times 72. And you do it again. 2 times 36. 36 is a perfect square. That's 6 times 6. But let's say you're still not thinking and you keep going. You just keep dividing by 2. That's 18. 18 divided by 2 is 9. 9 can't be divided by 2, but that is 3 times 3. So that one took a while, and you can certainly do it because it took a lot of lines to get it done, but it didn't take me that long to think about it. What I want to do now is I want to go back and find all the partners. So that's a pair. Here's a pair. This little 2 is not going to have a partner, but these 3s do have a partner. So I get to take out a 2, another 2, and a 3 plus. There's already a 7 in front. So 7 plus a 2 for that pair, another 2 for that pair, a 3 for that pair. But this guy didn't have a partner, still underneath the radical. So now I have to do 7 times 2 times 2 times 3. And the best way to do all of those steps is to go back to the Desmos calculator. 7 times 2 times 2 times 3. 7 times 2 times 2 times 3. That's 84. So my final answer right here, that equals 84 radical 2. Now let's step back to where I started up here, where I said, you know, when I look at this, I actually do think of 144 times 2. And I know 144 is 12 times 12. So I automatically have a pair of 12, which I would take the 7 that's already there. And I would take the 12 that I just got and leave the 2. But guess what? 7 times 12 is 84. So either way, whether you spread it all the way out, all the way down to prime numbers, or if you spot the perfect square along the way, I spotted the perfect square 12 times 12 a little bit sooner, you still get 84 radical 2. This is the last example for the video. So you will be doing Delta Math next. So log in and get started. If you're at home and you get confused, please log into Zoom to do a couple of examples with me to clear things up. If you're in class and you get confused, just raise your hand and ask for help. so that you do not spend too much time on this first assignment with radicals.